Hey everyone, what's going on? I wanted to take a look at this distributed load problem in two different ways. So the two different ways that I see intuitively to divide this up would be, so I have another picture. The first one would be to have two areas. Let's go with our yellow area. Let's go with the green. Our yellow area is going to be this rectangle here. And then the second area I would see would be a triangle. So we'll call this can be I'm going to go area 2 up top. And I'm going to call the bottom one area 1. Okay. So the other way that I see we could do this, the next one that's most obvious to me, and that you would see most frequently in like textbook solutions or online solutions, would be to have, with this green one over here. Oh, I almost went with the same thing. To go with two triangles though. So one bottom triangle. Let's even picture. Let's go with the pen for this one. Cut all the way down to here. Okay. There we go. So now we have two triangles. We'll highlight to make it a little clearer. So we have our green triangle at the bottom. And then let's do a blue triangle on top. Okay. So in this case, let's call, these are two different problems, right? And we're going to do two examples of it. But just to keep everything clear, I'm still going to name them differently. I'm going to name this one area 3 and area 4. Okay. So what do we want to do with our distributed load problem? So the first thing you want to do is turn your distributed load, or let's not say turn it, we'll establish your distributed loads point force equivalent we're going to start with point force equivalent. I'm going to put an S in parentheses. Depending on how the question is phrased, you may need to find the equivalent force for the distributed load, or if the question just asks for reaction forces, if we come up with 2 point force equivalents, so we would have 1 point force equivalent for A1 and 1 for A2 in this case, we could solve the problem using that without finding their single point force equivalent. So I guess our either way, the next method would be to do, you're going to create your free body diagram for your modified or simplified system, point force equivalent system. Okay. Then we can go in with our standard equilibrium equations. Okay. You're going to have kind of some substeps. So we'll call it 1.1. You want to find the area under the curve. or the area under the, we'll not call it curve, we'll call it the area under the force profile. So the force profile is using the height of your, or the magnitude of your force, times its length to figure out the point force equivalent. So the area, so area we use kind of figuratively, but if you were to represent this as a triangle, this bottom part as a rectangle of height 15 newtons per meter, going through a length of that full 8 meters, that would be that conceptual area that we're talking about. So the area would be the magnitude of your point force equivalent, or point force equivalent for that portion of the distributed load. The area will be the magnitude, the force magnitude for your point force equivalent. Within that, so let's start with that over here. We're going to have A2, the area. Let's do area is going to equal, let's start with A1. For A1, the area is going to equal the base times the height. So we're looking at this bottom rectangle. So I'm seeing a base of 8 meters times a height of 15 newtons per meter. So newtons per meter times meter, that's going to give us a final answer of newtons. 120. 20 newtons. So the equivalent, if we wanted to represent this bottom rectangle A1 with a point force, that point force is going to have a 120 Newton magnitude based on conceptualizing that profile as an area, right? So then if we look at A2, the area for a triangle is going to be, let's do that. The area for a triangle is going to be equal to 1/2 its base. So again, the base is going to be our 8 meters here times its height. The height in this case is going to be only the height of that orange section. So we already counted for the bottom 15 newtons per meter in our first shape. So the height of this triangle is going to be 40 minus 15. And that will get us 40 minus 15 times 8 divided by 2 would be 100. 100 newtons. So the equivalent point force magnitude for that A2 area is going to be 100 newtons. Let's then look at our eccentroid is going to tell us where these forces are acting. So I want to find the eccentroid of each of these areas. So the eccentroid for area 1, let's call that just x1, is going to be the eccentroid of that shape. So for anything with a line of symmetry, or centroid's going to fall in that line of symmetry. Rectangles are pretty easy because it's just the halfway mark. So if we have a base, of 8 meters, that eccentroid is going to be the halfway point. It's going to be 8 divided by 2, or we're going to have a 4 meter eccentroid for A1. What this tells us is that the point of application of this 200, 102, so we can call this now, so area 1 we could also call it force 1. Area 2, we could also call force 2. Point of application of force 1 on the equivalent system or within the equivalent system. So for our x-centroid for our triangle, 4 triangles, struggling, hold on. The x-centroid is at the 1/3 mark. It's going to be 1/3 closer to the longest edge. So in this case, if we consider our A point, our origin point, or our x equals 0 point, it would be 8 meters divided by 3, which would be 2 2/3. This would be our point of application of force 2. If we wanted to represent this one, this figure, this representation of it as, let's not do that. So if we wanted to simplify our distributed load to be a point force, which makes it easier for us to analyze, we're going to have our bar. We're going to have A over here. We're going to have C over here. We're going to have a pin joint at B. At a pin joint, we're going to have both an X and a Y constraint, meaning it's preventing motion in both the X and the Y direction. So I'm going to call this BY, and I'm going to call this BX. At C, we have a roller, so we're going to have only a perpendicular force there, CY. And then we can add in our point force equivalents that would add up to this final piece. So we have a 120 Newton force at 4 meters at that halfway point, so it's just beyond this. It's 1 meter beyond this. It'd be our 120. Assuming this is 1. And then the other one is going to be a 100 Newton force at 2.6. So it would be right before this B, these B's, we would have a 100 Newton force. If you wanted to go starting from there and analyze your system like that, you could. The other thing you could do is you could find the point force equivalent of both of these combined. So to do that, we're going to use our find a centroid of a combined shape equation. Let's add some text here. So our equation for that was that the x centroid of the system, or we call that big X bar, times the sum of the area or the total area of the system. We're going to set that equal to, let's say, we're going to set that equal to the sum of all the individual X bar times A, individual X centroid for an individual piece. We'll call it part. Times, within that summation of the individual part times the area of the individual part or portion. So if we would look at this, let's put it in a table. Sometimes tables can be easier to see. So we're going to have name of, let's go area, X centroid, and then X So x times a is going to be the eccentroid times the area. So then if we look at area 1, area 1 is going to be area 1 is going to be an area is going to be that point force equivalent of 120 newtons. Our eccentroid of that is going to be our halfway point, that 4 meters. And our x bar times a is going to be those two values multiplied together. So 120 times 4 is 480. Okay. For our area 2, let's go in here. Our area for that is going to be that 100 newtons. Our eccentroid for that is going to be 2 2/3. And so 2 divided by 3 plus 2 times 100 newtons is going to give us 260. I'm going to round to 267. Okay. So then when we go into here, our equation is going to have the x of the system. That's what we're looking for. The eccentroid of the system would be the total point force equivalent times the area of the total system, or the complete point force equivalent. Well, this area is force. Okay. So this value is going to be the sum of these two values. So it's going to be 220 newtons. It's also going to be our summation of forces in y, just for that, just for the point force equivalent. So if we were to turn both of these into a single point force equivalent, it's going to be a magnitude of 120 newtons. Over here, let's add these values together. So we have 480 plus 267. That's going to be 747. 747. 747. So if we went back up to this equation, we could find that the eccentroid of the system, or big X bar, is equal to our little x bar times a, or that 747, divided by that 220. And we would find that the point of application of that, so the 220 being the summation of area, so the point of application, if we were to find one single point force equivalent, this 220 Newton force, the single point force equivalent would be acting at almost 3.4 meters. We would expect it to fall between both of these two values. 3.4. Okay. This means that we could also we also could have solved this by doing just one single analysis of 1.4. So at our 3 Newton mark, we're going to have our By and our Bx. And then 0.4 from that, we're going to have a larger force, a 220 Newton force. Well, I don't know that it's larger yet, but a 220 Newton force over here. We're going to find out that it is larger. A 220 Newton force over there, and then we're going to have a value for Cy here. So now if we wanted to do our summation of moments about point B is where I'm going to start. It's going to be equal to 0 because we're in equilibrium. Bx and By, if we're analyzing point B, their moment impact is going to be 0 because there is no perpendicular distance. Moment equals force times perpendicular distance. So those two would have no impact. This 220 Newton would have an impact. So 220 Newtons is going to be acting at perpendicular distance of 0.4 meters away from point B. If we were fixed at B, this 220 Newton force would cause a clockwise motion. So in our class's convention, we consider that negative. The other moment impact that we're balancing that with would be our Cy. Cy is going to oppose that motion, so that's going to be a positive Cy times the perpendicular distance. Cy is at that full 8-meter mark. It is 5 meters from B, so the perpendicular distance is going to be 5. So then we can solve for Cy being 220 times 0.4 divided by 5, 17.6. So Cy equals 17.6. Newtons. We could then go in, either do another summation of moments, do summation of moments about Cy, or we could go in with I like to go in then with our summation of forces in X and summation of forces in Y, just because I think it's what we're most used to. So forces in X, summation of forces in X is equal to 0. The only X force that we have here is Bx, and therefore Bx must be equal to 0. The last equation that we'll throw in is our summation of forces in Y is equal to, our summation of forces in Y is equal to positive By minus 220 plus Cy, and all of that needs to equal 0 to keep our problem in equilibrium. That'll give us that value of, well, we have Cy is 17.6. So we have 220 minus 17.6 is equal to 202. So By should be 202 here. Around 202 Newtons. So our reaction forces would be Cy, Bx, and By. Let's go back over to our other example and kind of just repeat the process. We could even stop here and kind of go with that value. Okay, so we have our two areas, A3 and A4. So A3 is going to have an area of 1/2 its base times its height. Its base is 8, and its height is 15 newtons per meter. Which will give us 60. So the point force equivalent of area 3 is 60 newtons, or negative 60 newtons. 60 newtons in the negative y direction. For A4, it's going to be 1/2 base times height. The value that's different here is our height is going to be 40 newtons. So the point force equivalent of area 4 is 160 newtons. These are going to act on their respective centroids. It's going to be the 1/3 mark. So let's start with area 4 is actually the one that is probably easier, slightly easier in this case. So centroid for area 4 is going to be for a triangle. It is at the 1/3 mark. 1/3 closest to its longer edge. So for area 4, it's going to be 8 divided by 3. 8 divided by 3 is going to give us that 2.67-ish location. So for area 3, our triangle is oriented in the other direction where its longest edge is at our farther edge. So if A is our 0 point, then it is going to be at 8 minus that 1/3 of 8, or 8 minus 2.67. To get us about 5.3. So x of 3 is equal to 5.3. We could then take these values and go back into this table and do this equation to find one single point force equivalent of the whole system. Some of your homework questions require that, and then you would just follow this same process. The other option would be just analyzing the system like this. So let's redraw our system with what we know now. So we have the first force we're going to hit if we're traveling from A left to right is at 2.67. We're going to have a force of 160 newtons. And then the next one we would hit would be at the 3 meter mark. Would be this force of By. There is again going to be a Bx on here, but summation of forces in x direction again is going to be equal to 0. We have Cy over here at the complete 8 meter mark. So this whole thing is 8. And the last thing we have is at 5.3. We have this force of 60 newtons. Same thing. Let's do this 5.3. Okay. Same thing. Let's go in with then our summation of moments about point B is equal to 0 because we are in equilibrium. Otherwise, we're collapsing. So we have this is a perpendicular distance. This 160 is a perpendicular distance of 3 minus 2.67. Right? If we're fixed at B, this would cause a counterclockwise rotation. And so we're going to give that a value, a positive value convention. Yeah, there we go. Nothing at B would impact it because it's a perpendicular distance of 0. Our 60 newtons is going to oppose this one. So that is going to be a negative 60 newtons. It's going to cause rotation in the opposite direction. Negative 60 newtons times 5.3 minus 3, right? That's our perpendicular distance, is the space between this and B. And then the last value that we have to, the last thing that's going to impact our moment at B is going to be Cy. If we're fixed at B, Cy will cause rotation in the same direction as this one, a counterclockwise rotation. So that's going to be our positive convention, positive Cy, times 8 minus 3, or 5 meters. It's a little clearer in here. 5 meters. This will give us a value of Cy. We could then go in with our summation of forces in x to get that Bx is equal to 0. I was hoping I could just change the color of it. This one, Bx. And then we could do the summation of moments in y to get the value of By. So it would be 160 plus 60 needs to equal by plus cy. The magnitude of by plus the magnitude of cy. All right. Let me know if you have any questions, and I will talk to you soon.